Taking a look at Chapter 18, Section 2, Problem 4, we're asked to calculate a line integral in R3. Our vector field is e to the yi plus the natural log of x squared plus 1j plus 1 times k. And the path over which we want to integrate this vector field is a circle of radius 6 centered at the origin in the yz plane, starting at the positive y-axis and traveling counterclockwise. No, it's traveling clockwise. My mistake. I'm so used to everything going counterclockwise. I just kind of automatically wrote that. So, it's going clockwise. Once, it's going around once. So what we're going to do is all the usual line integral things. We're going to parameterize the curve. We're going to evaluate the vector field at that parameterization. We're going to take the derivative of the parameterization to fill in for the dr. Then we'll calculate all those dot products. So let's do all those things. We have a circle on this curve. On this curve, the x is always going to be 0. So points on this circle, the x coordinate is always 0 because we're in the yz plane. So let's write our parameterization. So it's going to be 0i. 0 because it's always on the xz plane. Now, points going around on the circle, we need to use, let's see, if we use 6 cosine t and 6 sine t, that would go clockwise around the circle. So here's the thing that we run into. There's an infinite number of ways to parameterize this curve, and we have to pick one. That's what we don't like about this problem. So any suggestions about how we parameterize the circle? If I do this, if I set it up as, let me do this as an alternate color. If I set this circle up as 6 cosine t, 6 sine t, this goes counterclockwise around the circle. Oops, let's say for t between 0 and 2 pi. That will go counterclockwise around the circle once. So what could we do? Well, one thing we can do is notice that we still want to start here at 0, 6, 0, and we still want the y's to go from 6 down to -6, then back up to 6. So this seems to work for y. I'm just doing yz at this point. So the cosine does the right thing for y, but 6 sine t would start off at 0 for the z, and then go up, down, and then up again. So the sine goes up, down, up. But we want the other way, down, up, down. So instead of, we want to start off at the middle still, but we want to go down first, then up, and then down. We want to break this, we want to imagine this motion in 2 components. We want to switch this over to Etch-a-Sketch mode. So our left hand is going to move left and then right, while our right hand goes down, up, down. So down, up, down. While our left hand goes left, right. So we want to make it go the opposite. So we'll adjust it to be yz is going to be 6 cosine t. That does what I want. And I'll just multiply the second one by -1. 6 sine t. Then I can keep my t between 0 and 2 pi. Can anybody think of another way to parameterize this circle so that we go around, oops, everything's moving, so that we go around the circle counterclockwise, or sorry, clockwise once? So that would be an interesting question to think about. How else could we have parameterized this circle? This is the method that I used. This is the first thing that occurred to me. I just wanted to change the up and down motion. So I just multiplied the up and down motion by -1. So let's see, 0i plus 6 cosine t times j minus 6 sine t times k. Any questions? So I need r prime to be my dr, so I need an r prime of t. Is going to be 0i again. The derivative of 6 cosine t is -6 sine t. The derivative of sine is cosine, so -6 cosine t k. And this will all be dt. And this is still t between 0 and 2 pi. So we need the vector field evaluated at these points. All right, so we need the vector field evaluated at all these points. I'm going to write that out separate. So the vector field is e to the y, and in this case, y is 6 cosine t, so here's my y. So e to the 6 cosine t times I plus natural log of x squared plus 1, so plus natural log of x is 0, so 0 squared plus 1 times j plus 1k. So this is what the vector field looks like. Now, if we simplify this part, 0 squared is 0 plus 1, we get the natural log of 0, we get no j component. So we end up with e to the 6 cosine t I, 0j, and 1k. In the line integral, we'll calculate the dot product of this vector and the r prime of t vector. So let's put it all together. The integral over c of f dot dr will be equal to, this is going to turn into the definite integral from 0 to 2 pi of e to the 6 cosine t I plus 0j plus 1k dot, then the r prime, 0i minus 6tj, oh, sorry, 6 sine t minus 6 cosine t k dt. I always use too much spacing at the beginning so that everything gets crammed up at the end. I forget how long line integrals end up being, especially because I always keep writing all the stuff, like the zeros. Because we're doing a dot product. And so the e to the 6 cosine t that we're like, oh, I don't want to integrate that. That looks terrible. Gets multiplied by 0. So that goes away. Then it's like, oh, we still got the sine times 0. Oh, that goes away. So all we left with is we're integrating -6 cosine t from 0 to 2 pi. So after all this, we're just integrating 0 to 2 pi of -6 cosine t dt. Remember, we're doing a dot product, so all these vectors drop down into scalars. The dot product of these two vectors is this scalar. And now we don't even have to find an antiderivative because we're going from 0 to 2 pi, and cosine starts and ends at the same place. All that, and we never even had to integrate anything. So, rad. Any questions? It's funny. So I just happened to look up the solution. It's like, oh, hey, what if I messed this up? So I looked up the solution because I have them. It's the power of being a teacher. And these authors just do weird things. Notice that in the solution, they factored out the negative, but they left the 6 in. What's with these people? Such a strange set of traditions and habits they have. Oh well. So all that work for 0. Let's pause the video here and do another problem.